After this video, you will never be scared about general solutions. When you have a trig function of x is equal to a and you want to solve for x, you usually just take the inverse, right? Wrong. This is only one solution. And in fact, it can sometimes be the solution you're not even looking for. You often want to find a general solution. Let's start with sine x. The first thing I'm going to do is write a as sine of sine inverse a. This is allowed because of how we define the inverse trig functions. Okay, so then just for clearing things up, I'm going to let y equals sine inverse a. So now we have sine x equals sine y. Okay, so now I'm going to think of every case in which this can even be true. The first possibility is x is equal to y. That's pretty obvious because that means that sine x equals sine y, right? X could also be pi minus y. Why is that? Well, sine pi minus theta is sine theta. If you want to learn the basic trig identities in just 4 minutes, check out the video in the description. Also, we know that sin x has a period of 2 pi, which means you can add any multiple of 2 pi to the input without changing the output. So let's apply that idea to both of these. We're just going to let k be any integer. This e symbol means is an element of, and this z just means the set of integers. So k is in the set of integers. Okay, so now we have 4 possible ways x and y can be related for their signs to be equal. But notice that the first two are given by the last two if we just take k equals 0. And we're just doing this for any integer k. So we don't even need the first two as separate cases. Now we just replace y with sine inverse a, and there you go, we have our general solution. This is often the most intuitive form of the sine solution, but the problem is it has two cases, so we can actually get a more simplified form. Firstly, we combine the 2k pi and the pi in the second case, and that gives 2k plus 1 pi. Notice that 2k plus 1 is an odd integer for whatever integer k you take. Also, 2k is an even integer for whatever integer k you take. Also, we know that minus 1 to an even power is 1, and minus 1 raised to an odd power is minus 1. So we can actually write it like this. Take a moment to check that this is the same as before. This first case works for any integer of the form 2k, that is an even integer. So we can actually write it like this, where n is an even integer. And we can do a similar thing for the second case. We have two cases for n even and n odd, but notice that the two expressions are identical. So we can write this as one case, but take n as any integer, since any integer is either odd or even. So sin x equals a implies that x is minus 1 to the n times the inverse sine of a plus n pi for any integer n. It basically just stems from the fact that sine pi minus theta is sine theta, and that sine has a period of 2 pi. Okay, now that we've done sine, let's go through the other ones much quicker. We write a as cos inverse cos a, and then let y equals cos inverse a, just to make things clearer. Okay, so excluding the fact that cos has a period of 2 pi, what are some ways in which cos x can be cos y? Well, of course, x could be equal to y, or x could be equal to minus y, since cos of minus theta is cos theta, as cos is an even function. There are no other identities like this, which allow you to change the input without changing the output, except the periodic identities. So now we apply those to these two statements, giving us this, for any integer k. Of course, the first two statements are given by the next two if you take k equals 0, so we only have these two statements. Now we can actually combine them into one statement using a plus minus. And then we just replace y with cos inverse a, and we're done. Cos x equals a implies that x equals plus minus cos inverse a plus 2k pi for any integer k. The general solution for tan is actually the simplest of the three. Okay, so we write a in this form and then let y equal tan inverse a. Tan x equals tan y. In fact, the only way this can be possible, if you ignore the fact that tan has a period of pi, is if x equals y. That's it, there's no other nice identities. So then we just apply the periodicity to this, giving us another statement x equals y plus k pi, since tan has a period of pi. And of course, k is an integer. The first statement is given by the second, where k is 0. So all we have is x is equal to y plus k pi, replace y with tan inverse a, and we're done. Tan x equals a implies that x equals tan inverse a plus k pi for an integer k. Okay, so here are the general solutions listed together. You just derive them by considering the different ways two variables can be related, so that when you take the trig function of both of them, you get the same answer. Here are the formulas if you have a trig function of x is equal to the trig function of y. These are just the formulas we derived initially. If you enjoyed this video or learned something new, please consider subscribing. It would be amazing if we could get to 1k subs.